thank my colleagues over here, especially Dr. Biju and his team, for inviting me to come over here. If you see the title of my talk is Symmetric Consideration in Indexing X-ray Diffraction. You know, X-ray is a very powerful technique that any material scientist or even structural biologist or chemist can't avoid using it. So it is that powerful, it is that unambiguous, that made it very popular. When the last year we celebrated throughout the world International Year of Crystallography. That was to mark the occasion of the 100th year of the invention of X-ray diffraction. Okay? And this year it is recognized as the International Year of Light. You see the electromagnetic spectrum here, it has various regions in which we see only a small region. Then you have several other regions which we don't see. We could experience their influence in different forms. They interact differently with matter. So we understand these radiations are existing. And X-ray is one among that, just between ultraviolet and gamma. And the useful X-ray that we expect is with wavelength of 1 angstrom. That is what we refer, we need for our characterization studies. Okay. So this is International Year of Light. Again, X-ray becoming a part of light is usable light. So it's okay for another year also to have some kind of celebration. Now, coming to the thing, wherever I go, being an X-ray crystallographer, I put this man's picture. You might be remembering who he is. William Mohanjan. He discovered X-ray in 1895, almost 150 years back, 120 years back. Remember, very next, this year 1895 he discovered X-ray. Very next year, radioactivity was discovered. And then 97, Thomson discovered electrons. So when he discovered X-ray, there was no idea about the nature of it. Even electrons were discovered a couple of years later. And the atomic theory that we see today, the Bohr theory came into existence only in 1911. So it was that remote. The idea was totally confusing on those days. So he put the name X, the unknown, to represent the unknown. And there are so many things which have happened in between. I will tell you the story. See, I can't teach you everything. That matter, nobody can teach you the subject, the full spirit. So what my aim is to make you interested in the subject. And I know that all of you are equally intelligent. You are interested to read more and try to understand. The moment you read more and more, you will grab more and more. Otherwise, it will become a waste. So my primary aim is to make some interest within you, some spark within you, that you could lightly get up at any time. Okay? So, of course, I will strictly come to the topic also. You know, it was 1895 X-ray was invented. It was on November 8. Okay? He was doing experiments through discharging electricity through gases. Fortunately, air doesn't conduct. Otherwise, we could not have pulled our electricity wire through air. We are lucky. We can draw it through air. So there is a factor. How we could make them conducting? What are the conditions? To reduce the pressure. That means you need to have very few molecules. They supply very high voltage. That will flicker the atom and give you electrons and then positive charge particles. They just move anions and electrons. Okay. They move depending on the energy of the slide energy taken from that slide voltage. That will lead to formation of X-ray. Okay? Then you see that immediately after the invention of X-ray, that came into applicable in biological science, especially in medical science. This picture that you see is the Bertha's hand, in which you have Bertha is the wife of Brongen. Brongen is here, which is a very primitive form of X-ray making. See the hand of Bertha with the wedding ring. And of course, this is the wedding ring which most of the people, the maximum number of people in the world have seen. Not the real one, but the picture of the wedding ring. Okay? And immediately it was applied after the invention of X-ray. Then you see, the fun is that the produced radiation is a very primitive form of X-ray machine. Then you see a physician here checks the backbone of a gentleman. He has a back pain. To identify there is some disruption or something, he takes an X-ray now. But those days, what to do? There is a machine which generates, which makes X-ray, and this physician is looking through a fluorescent film. And now we know how dangerous it is. Okay? But immediately after the invention of X-ray, the hazardous effects of X-rays were not known. That was the fact. If you look at this, the skin, that was 1500 times higher than the dose of modern X-ray equipment. Right now, whatever X-ray equipment we have, the intensity of the beam that came out from this will be 1500 times higher. Okay? Exposure time is decreased from 90 minutes to about 20 milliseconds. That was the story in 2010. Now the technology has advanced further, so you need still less than time. So if you want to have an X-ray of your hand, you keep roughly about 90 minutes on the X-ray beam. The technology was that bad. But now you see that in modern laboratories, the X-ray equipment, and how the sophistication, how much the sophistication has involved in it now. And again, okay, that is the story. Okay, you see that very primitive form of the application of X-ray, but it was applied immediately after it. Now there are several fields in which X-ray could be applied. We have seen medical imaging, then CT scan, that's even another type, and then nature of sample. Any kind of material scientist, if you have a sample, you take this to X-ray, it's a non-destructive testing, you get the sample back, and you can analyze whether the sample is that you expect or not. Then you can, if it is a crystalline material, you can find out the cell parameters, A, B, C, alpha, beta, gamma, that you know, you can easily find it out. Then the particle size you can analyze, that is the grain size. For stress, whatever stress in the lattice you can estimate, then you can characterize it, that you know. Composition and purity, if you have a mixture, you can find out the composition exactly, very precisely you can calculate. So that will tell you how pure sample is your sample. Okay? Then, suppose the material like barium titanate, you study in your MSc classes that it undergoes several phase transitions, along with the structural transitions, where the structural transitions are responsible for their physical transition, phase, property transition, parametric property. Okay? So you can monitor phase transition. Then thermal expansion. You very well know that when you heat it up, any substance will expand. You can monitor how much it expands. You know the volume of the unit cell. You can calculate with temperature. You can easily find out the thermal expansion. Then of course, as I said, it's a non-destructive testing, widely used in industry, especially in metallurgy, to find out some cracks or something. When you make some lab of material for some particular application, you take an X-ray, you know whether cracks or something inside could be easily identified. Then there are so many other small angle X-ray scattering, wide angle X-ray scattering, grating incidence X-ray scattering, etc. So many other techniques are developed. Then these are all characterization techniques. These are generally used. Then when you come to other side, the structural determination. What is the structural determination? Imaging of a molecule. What do you mean by imaging? To find out the exact atomic positions where they are, you will also get some kind of vibrational motions of those atoms. That is what is structural characterization. Then when you have single crystals, when you have powder, the methodology is almost the same, except for few different. Okay? So you can have several methods to find out the structure of single crystals. You know, a crystalline material is a three-dimensional object. So you need to have a three-dimensional set up to collect the data. Otherwise, it becomes incomplete. But when you have a powder, the sample is very minute that you cannot use as three-dimensional measurement system. Therefore, we go for one-dimensional measurement system. That is the limitation of the powder crystallography. And the dual crystallography, the glucose diffraction method is that you will get the precise data every direction. So that makes it easy for your analysis. And you have several methods which I don't go into the details. When you have powder, you have a ritual refinement technique. What is the ritual refinement? It's just a refinement. You know something that is existing and you have a data. And you know that your data is going to be relevant with some particular system. For example, barium, titan or perovskite structure. You modified it with some phase. You know that little bit of deviation you can expect from the actual barium titan structure. Then you know that information from chemistry or some intuition. Then you put that value and do the recalculation and check with the data because there is agreement to say that this is perfect. That's only a refined technique. Or you can also follow the single crystal, similar to single crystal method when you deconvolute the peak. What is the deconvolution is that in single powder XRD, a single peak appears. Okay, I'll tell you that later. A single peak appears. It is not from a single HKL plane. It will be a combination of several planes. Okay, so it's a convoluted signal from different HKL planes. If you deconvolute it, then that becomes equivalent to single crystal data. Then you can follow all these methods, what are these applicable for single crystal. People are doing it now without any problem. Okay? Then there are several spectroscopic techniques, XR, absorption spectroscopy, photoelectron spectroscopy, X-ray fluorescence, energy dispersive X-rays, scattering, etc. So many techniques have developed just based on little man's invention. And you know the story is that he died of extreme poverty in 1923. People asked him to patent his work. He said, my invention was quite accidental. Let it be useful from the humanity. He did not patent it. And after effect is that he died of extreme poverty in 1923. Now people go for each and everything, whether it is useful or not. You pay to the patent office of the United States, get the patent. They are happy to use that. But nobody will buy it. Otherwise, if you don't buy it, it becomes a waste. Anyway, this is how you generate X-rays. You have a cathode which emits electrons and very high. You accelerate it to 35, you have electron volt. For example, for molybdenum, it falls on a target, you get X-ray. You have two types of X-rays. One is continuous X-ray, when fast-moving electron falls on the atomic field of an atom, that will be decelerated and it has to emit radiation. That accounts for the continuous X-ray. And suppose electron falls on an atom and it knocks out an electron from a particular orbit, that will be killed by another electron from a higher orbit. That gives out a photon which is characteristic of the element. Okay? So that is characteristic of the element. It is the energy difference between two energy states defined by Bohr theory. That cannot change. Okay? So every element, atomic energy states are precise. Therefore, the characteristic radiation emitted from every element is unique. And this continuous X-ray looks like this. This is the continuous background, and this spike represents the characteristic state. Okay? So what we use generally in our X-ray diffraction experiments, we use molybdenum. This is 0.71 angstrom. We have copper. It comes out to be 1.54. Cobalt, iron, chromium. When you want higher and higher wavelengths, you need to go. Practically, we use only up to chromium. You want to have a very high wavelength up to 0.29 angstrom. For our normal purpose, for characterization or ordinary things, what we require is molybdenum, copper. These are all for macromolecular data collection. Very rarely used. Okay? So, this is how you have two sets of X-rays and that could be differentiated. Now, the story is that this is the man in 1940. Actually, in 1912, he invented. He was very curious to put filters on the X-ray. Before that, nobody did. When he found that when he aligned the single zinc sulfide single crystal onto an X-ray beam, the result was quite surprising. He got a pattern like this. You keep a photographic plate and you kept a zinc sulfide crystal in the beam, X-ray beam, and you kept a photographic plate, what he has seen is a picture like this. Instead of seeing the molecules, what is made of, what with which the zinc sulfide crystals are made of. But what he got is this. What is the relation between the crystal and this kind of a diffraction pattern? That is the question. Okay? He made some kind of answer. The Lavey equation, which you are very familiar. Okay? What is it? You have an array of atoms, say one dimension. You take this, repeat A, wow. And this is the incident wavefront, X-ray plane wavefront incident like this, and this is the scattered wave. You know? Then what is the path difference? The difference between these two is the path difference between the two wavefronts. Okay? This vector, when you project onto this is A cos alpha, no? Alpha, and this will be A cos alpha, no? This is the incident. So A cos alpha minus A cos alpha naught will be the path difference between the two plane wavefronts incident. What is the principle of superposition in optics? If the path difference is an integral multiple of lambda, you get a constructive interference. Okay? So same condition we use. He said that the path difference is an integral multiple of lambda. H is an index. So take plus minus integer values both plus as well as. Okay. Then if you have a second dimension, you can put like this, and third dimension like this. You will say crystal because it is a triply periodic system. You can have three sets of arrays. You could get this kind of an explanation which is satisfactorily given by Lavey, for which he was awarded the Nobel Prize in 1940. Okay, I think this is clear. Later, in my talk, what I am going to specify is what is the relation between the crystal and this kind of a diffraction pattern. Okay, now these Lavey equations are very popular on this thing. In 12 to 13. What the picture is shown here is Sommerfeld explaining Lavey equations in Royal Society and so many other places, scientific bodies he has explained. The invention was that important. Sommerfeld, you know, the man for elliptical constructed atoms and so many. And then immediately after that, these two people came with a very simple explanation. Bragg and Father Bragg. This is the only event which both son and father shared a Nobel Prize. Okay? That's only unique event. Then what they did for their service in the analysis of crystal structure by means of X-ray, they gave a very simple explanation how the diffraction takes place on a crystal and how it could be accounted to find out the molecular naming of the structure, to find out the structure of molecules. Okay? So this is the, if you imagine two sets of planes, separation D is the real space, this is the incident wavefront and this is the scattered wavefront. What you could find is this much 2d sin theta, n lambda, is an integer, and what you can get is the Bragg story. The very same thing what Bragg said in a different step. They also said the same thing. But what they did was they applied this to find out every reflection from where it occurred and how you could get the flux. That was there. Only after that, 1915 only you could identify sodium chloride, potassium chloride, diamond. There are very beautiful crystals. You eat every day sodium chloride. You will be very curious to know how the sodium and chlorine is arranged, whether it is together or separated or how it is arranged. But no idea. The diamond is very beautiful. People do wear. How the beautiful faces come into, how it is scattered, how it is beautiful, why it makes so beautiful, why it is so rigid. It's a form of aluminum of carbon, isn't it? Grease is also carbon. Grease is just a lubricant. But diamond is cut glass. That hard. And again, several other forms are coming to isn't it? So there are several forms. Why they are different? It is basically the structure or the chemical bonding, how one atom is bonded to other atoms means the physical property as well as the chemical properties of the molecule. That's the of it. And when you say this one, what you need to remember is in the ordinary scattering process or reflection, what you use is this angular incidence. Okay? Normal with the plane. Here we always use the grazing angle. What is that? Incident beam and the plane scattering. So it is 90 minus theta the other way. That's the catch which you need to remember. And again, when you look at this equation, what is the possibility maximum value of lambda you should use? What is the value? Theta, the maximum possibility is 90, that reduces 1. 2d is lambda for n1. That is the limitation. What is the limitation? Could you use any lambda for XRD diffraction? As per this equation, look. Could you use any wavelength for XRD diffraction? No. Diffraction is possible only if the maximum value should be twice the interatomic space. What is interatomic space generally? 1 to 2 angstrom. Hydrogen or carbon is 0.8 angstrom. Generally, if you have metals, it comes around to be 2.1, not more than that. So that's the maximum value. What is D? D is the interplanar spacing. That is decided by the materials. We have no control. So all the materials do have this kind of a displacement between the distance between the two set of planes. Therefore, the choice of lambda is limited to 1 or 2 angstrom. That is why we use in the previous slide I said those are the radiations we could use for X-ray scattering experiments. Okay. Now there is another thing that you need to remember is that, do you remember about Mosley? Who is he? Tell me. Mosley's spectrum, characteristic spectrum of elements. And he is the man responsible for the arrangement of periodic table, the modern periodic table. So Mendeleev arranged most of the elements in atomic, the increasing order of atomic weight. But when he looked at the X-ray spectrum, characteristic spectrum of various elements, he found that atomic number is much more important than atomic weight. So he could arrange every element still be followed without any problem. That's the modern periodic table. And if you look at Nobel Prize for 1916 in physics, not given to anybody. Still it is blank. Says that 1914 the First World War came out, broke out in 1914. Okay, he went for the war front. Decided to go to the war front and he was killed with it. And 1916 Nobel Prize was actually meant for him. Recommendation from the recommendation of the Swedish Royal Committee was to award the Nobel Prize for this man, but unfortunately he was killed in the war front, and there is no custom of giving the Nobel Prize after that. So it's still blank. Okay, those are all the stories. How people have spent their life for science. Those people did not get much, but their invention we make use of it. Now, look at this, as I said earlier, this is crystal and this is the diffraction pattern. What kind of a relation between these two? That was the important thing for which Dewey was given the Nobel Prize. Okay? You have a lattice and a basis that leads to the crystal. What is the lattice? What is the lattice? It's an arrangement of, periodic arrangement of points in space. Is that complete? No, it's not complete. Every point in the lattice is related with every other point in the lattice by a translation vector. So if you have a point, if you know the translation vector, you can generate the entire lattice by putting n1, n2, n3 as plus minus values, integer values. The A, B and C are the repeat systems. That's a lattice. Don't say that's simply an array of points. But an array of points, the unique relation of a translation vector defines a select lattice. Okay, so in the real space, in the real space, you have a lattice attached to every lattice point. You have a basis. Basis could be an atom, or a group of atoms, or a molecule, or a group of molecules, whatever it is. You attach at some particular point something, then to every lattice point you should attach the same thing. That's only it. Okay, now what is this? This is the diffraction from exoskeleton. Looks entirely different from this. Where you have a lattice, again, if you look at this, some of the intensities are absent. You have a lattice. Okay, it's just lattice like this. With every lattice point attached with the intensity. Okay, this is not in the real space, this is in the reciprocal space. Whereas this one, you see it in the real. Okay, so the basic concept is that diffraction takes place in the reciprocal space, or the diffraction pattern will give you a map of the reciprocal space of the real crystal, where the reciprocal lattice is attached with intensity. That is the basic concept. The real space, you have a lattice plus basis, whereas in the reciprocal space, you have a reciprocal lattice plus intensities as the motif or the basis. That is the basic concept. Okay, what is the reciprocal lattice? Every real lattice has a translation vector like this. You can have a corresponding vector in the reciprocal space and you have a unique relation between real and reciprocal parameters that is worked out and given in the test. You put by some name A star, B star and C star, where A star, B star, C star are the counterparts of the ABC in the reciprocal space. Okay, so there exists a unique relation between real cell parameters and reciprocal parameters. When ABC and alpha, beta, gamma of a unit cell is defined, then the reciprocal lattice is also uniquely defined. Okay, there is one-to-one correspondence. For simple systems, the real space it is A, in the reciprocal space it is 1 over A, 1 over B, 1 over C. Okay, so that is the relation, the simplest between real and the reciprocal space. So I will elaborate a little more. A reciprocal lattice and real reciprocal crystal. A crystal resides in the real space. Now continue. In the real space, visualize it. The diffraction pattern of the crystal resides in the reciprocal space. Okay? A diffraction experiment, reciprocal space is usually sampled. Then, from the real lattice, the reciprocal lattice can be geometrically constructed. Okay? Then, the properties of the reciprocal lattice, they are inverse of the real lattice. Then a real crystal can be thought of as a decoration of lattice with motif. Crystal plus motif, lattice plus motif. Reciprocal crystal is utilized as a reciprocal lattice decorated with motif of intensity. So intensities are the motif in the reciprocal space. Or this space we call it as the Fourier space. Are you familiar with the Fourier transform from real space? If you take a plane wave equation, what do you write? Y equals A raised to I theta. Or more generally, I k dot R. R is the vector in the real space and K is the vector in the Fourier space or the reciprocal space, where we call K as the propagation constant of the. So through which space the wave propagates? Through the Fourier space. Okay? That is how you take the relation between Fourier transform, Fourier FT IR and real IR. Okay? One is in the frequency domain, other one is in the 1 over frequency domain. That's it. Okay? Again here also you get the same concept. The diffraction takes place in the reciprocal space. Because the plane wave propagates through the reciprocal space or the wave space. That has the same properties of that of the reciprocal state existing in the crystal. So you map only the reciprocal state in the crystal. You might have taken 10, you will get a 8ds spectrum. Electron diffraction spectrum is enough. What do you get there? You get a spot similar to this. That is electron diffraction. X-ray of the case is electron diffraction. Any diffraction process will give you information about the reciprocal state. You get only spots there, which you index. Okay. Fine. Some more point you need to remember. The reciprocal of the reciprocal lattice is the real lattice. Okay. Plane in the real lattice becomes point in reciprocal lattice and vice versa. Yeah, when you have an scale plane. What is an scale plane? It is an address of a plane, crystal plane, right? Karyavattam campus. Okay? Karyavattam PO, Karyavattam campus, physics department, only address. Same way, one plane in a crystal has a unique address. So major indices are the address of the plane. Okay? No, I mean, it's an address. You say 211 is a different plane, address is different. Like that, a plane in a real lattice becomes a point in the reciprocal. 111 plane, the real space is represented by a real space. When it comes to the reciprocal space, it reduces to a point. That is the concept. Okay. Now, to summarize, I think I can take more time in this because I aim is to get the concept for you. Okay? Doesn't matter. So when you have a real lattice, what is it? Decoration of lattices, motif will give you a real system. Then a reciprocal lattice is purely a geometrical construction. Nothing like that, but you construct it. Imagine. Then you decorate the lattice with intensities, you get a reciprocal system. Then you get the diffraction pattern from that. Then you expose the exchange or electrons or whatever. And then the question is, in crystals based on particular lattice, the intensities of particular reflections are modified. In some cases, they are missing. The question is, how many reflections you can get? What are the type of reflections you can get from the crystal? What is the criteria? How do you understand? How do you explain? These problems could be answered from wall sphere construction. Okay? What is the wall sphere construction? This is the gentleman's. I think I rate this one really much more significant than the other two. This one, reciprocal lattice. Okay, what is the concept? He introduced the concept of reciprocal lattice into the real lattice concept to explain Braggs law. The process of diffraction or the process of scattering from a crystal is explained in terms of reciprocal space. Okay? Just keep it the real lattice concept, then introduce the reciprocal lattice idea together with this to explain the simple diffraction process. That is what construction is. We will look into the next one. You see that? Imagine a sphere with a radius of over lambda. What is lambda? Lambda is the wavelength of the radius. To take a sphere with a radius 1 over lambda. That's in the reciprocal space, isn't it? Okay? So you have 1 over lambda as the radius, then the sphere is just imagined. Then X-ray incident in this direction like this. It comes into and it goes out, and you keep a crystal at the center of the sphere. Okay? Suppose the diffraction beam comes out from the point C along the radius vector direction. So this red arrow shows the direction of the diffraction beam or the reflection beam or whatever it is. Okay? Now, this is the diffraction beam and this is the incident. The angle is 2 theta, you have to continue. Like that, whatever it is. Let it be taken as 2 theta. Okay? Now, we know that if we keep a crystal plane like this, then the plane should be bisecting the angle of the incidence and the angle of scattering. The normal principle of work. So the plane should bisect the incident and the scattered beam. Angle made by those. So that is the geometry. Now, see that, okay, coming to the next. See, here I have a reciprocal space. See, the crystal is there, this is the beam, this is a scattered beam. You have a reciprocal lattice space. And the origin of the reciprocal lattice, let this be the direction in which the X-ray beam exits through the sphere of reflection. Okay? This is a cross section of the sphere of reflection. It looks like a sphere, it looks like a circle. Okay? So, like the real lattice, you have a reciprocal lattice. Agree? Follow? You have a real lattice, it's an array of points, two dimensions, an array of points. Can you just imagine, let's take you this. This is a two dimensional lattice. With motifus is human. Now, similar lattice is there, what I have drawn in like that. It's a reciprocal lattice, it's not in the real space. Therefore, I put points as the reciprocal, intensities of the reciprocal lattice, points are given equal intensities distribution to every point. That is how we constructed the reciprocal lattice there. Let us imagine this is the origin of the reciprocal lattice. Okay? If you do the translation vector, you can generate everything. Now remember that this is the origin. Suppose there is a reciprocal lattice point on the surface, touching the surface. This is the direction through which the X-ray beam comes out. Okay? Now we will go back to the previous slide. So this is the origin of the reciprocal lattice. This is the point. So there is a point P on the surface of the sphere through which the scattered radius comes. Okay? Now listen, this is the origin and this is another reciprocal lattice point. What is the vector OP? It's a reciprocal lattice vector. Isn't it? Any two points are connected by a vector in a three-dimensional space. Fine. Any two points are connected by a vector. That's in the real space. Reciprocal space is also you have the same thing. So these 2 points are connected by a reciprocal lattice vector. What is it? It's given there. What is the dimension of the reciprocal lattice vector? It's 1 over d, where d is the spacing in the real lattice. Agree? So it has to be 1 over. So this spacing is 1 over d. So take sin theta. Okay, we will remember this geometry. Come to the next. Okay, this is the incident beam. This is the crystal plane, goes like this. This is the incident, and this is scattered, and this is the other one. Okay, you have here this, and this. This is the bisector of the. This is the crystal plane that bisects exactly 2 theta. Coming to the next. Same thing is repeated here. Okay, this is the incident direction, and the magnitude is 1 over lambda. Again, the scattered vector also will have the same magnitude, isn't it? Because it is the radius of the sphere. Okay? This is the incident beam, this is the scattered beam. Both represent the radius. So it should have the same magnitude. What is that? 1 over lambda. This is 1 over lambda. This is 1 over lambda. Of course, this should also be 1 over lambda. Okay? So come to that. This 1 over lambda, this is 1 over lambda. This bisects, so it makes angle theta. So what could be? This is the vector, reciprocal lattice vector. And what could be this? 1 over lambda into sin theta. Sin theta will be opposite side by this side. Okay? So this side will be 1 over lambda into sin theta. This is the unit vector. Similarly, you have same thing, 1 over lambda into sin theta. So what could be the total length of the reciprocal lattice vector? 2 sin theta over lambda. That is the magnitude of the reciprocal lattice vector. What is it? It's 1 over d, as I said earlier. So what do you could get? 2d sin theta equal. What is it? Again, right. So what you all did? It took the concept in the reciprocal space, introduced with the real space, and got the same explanation for scattering, that is fraction. Okay? So it's very clear now. So I have a small animation to tell you how the diffraction takes place. Oh, okay, start. So there is I have kept a photographic film there. X-ray beam ports like this, and what is the condition? The point which should be on the surface of the sphere. Then only the geometry will be satisfied. You get the radiation coming out like this. Okay? Then when this on the surface you get the this one. See, you get the radiation. Now this one. Whenever a reciprocal lattice point which touches the surface of the sphere, the geometry force diffraction is satisfied and you get the scattered radiation radially coming out to the point. Okay? Follow. This is the concept of X-ray diffraction in terms of the reciprocal sphere. Look at this. Falls there, another one falls there. Okay? Like that. But remember that there are several lattice points falls on the same geometry, giving you the scattering in the same direction. Okay? That is what is multiplicity. So several HKN planes giving you the scattering in the same direction. That is called as multiplicity. Anyway, I don't have time to go into those details. But I think this is the scattering process. What is the condition? The difference between the incident scattering vector and the diffracted scattering vector should be a reciprocal lattice vector. This and this, the difference between the two should be this. That is the concept. Delta K should be a reciprocal lattice vector. In phonon scattering also we take zeta. Phonon scattering. What is the first? The bluing zone. Then K satisfies minus pi by A to plus pi by A. What is pi by A? What is pi? The periodic factor. Take 1 over A, minus 1 over A to plus 1 over. What is that? The bluing zone, where Bragg law is satisfied. What are the bands in band gap in semiconductor physics? The Cronin-Penny model. It's an one-dimensional periodic motion of electrons through a crystalline pattern, where the wave solution cannot exist at certain points when at its own boundary. You have the first band like this, at pi by A minus plus pi by A has a gap, then it again comes out like this. Second band, minus 2 pi by A plus 2 pi by A, another band, second zone boundary. The Bloch theorem again takes to the same thing. Okay? To understand this concept, you understand so many things. And phonon diffraction, everything, phonon scattering, everything. So delta K should be a reciprocal lattice vector for maximum scattering intensity. Okay? Band theory is no way different from this. Where the zone boundaries, you get the Bragg. And again, anything that goes out, you have a reduced representation. The vector goes out of the real bluing zone, you put back by adding a translation vector. That is about theorem. Okay? All these are methods. So, okay. Now, you might have observed diffraction phone. How do you get phone? In powder diffraction. It's a good difference. But when you come to powder, this is the sphere of reflection. This is the incident beam, this is the scattered beam, this is the crystal plane, and this is the circle containing the plane containing the crystal plane. Now, this is a reciprocal lattice vector, is it not? The P is on the surface of the sphere. Okay? Look at this, in a powder pattern, all orientations of the crystal plane, you have very minute crystallites oriented in all possible random directions. The size of the crystallite is very small, that's the only difference. But it is oriented randomly in every direction. That means every theta, you have some planes giving you scattering. You get a scattered vector. Okay? So the locus of OP, the vector OP, what is it? It's a sphere of radius over the space. Agree? Because you have very minute, number of millions and millions of very minute crystallites oriented in all directions. If a crystal plane is like this, the vector will be like this. Another plane is like this, the vector will be like this. You have all possible orientations of the minute crystallites. So that the vector will represent a sphere with radius OP. Right? So what is the intersection of this sphere with this? That is our condition. Okay? For Bragg's law to be satisfied, the point should be on the surface of the sphere. Then only the geometry will be satisfied. So this sphere intersects with this evolved sphere, giving you the circular section. Okay? and the beam comes out in our diffracted beam comes out through the periphery of this circle. So in effect, what do you get is a cone like this. Okay? The intersection will be a cone like this. So diffracted beam emerges from the crystal as cones. In any one you get one set of cones, two you get another set of cones, concentric cones. In three you get a third set of cones. And then takes negative values, direction of the cones will also be reversed. You get back scattering. Okay? Forward scattering when n is positive, and your backward scattering when n is negative. So this is the basic thing what you could get in a diffraction sequence powder diffraction. Okay. Now again, as I told you earlier, there are few reflections missing. Look at any diffractogram. Look at all these X-ray scale planes are possible in a innumerable number of scale planes are possible in a crystal. But do you get that many kinds of diffraction intensity? The answer is no. Why? That is given again by all the constructs. Look at this, you have an aluminum crystal. Say, you know how to index it. I don't have time to go into those details. Okay? You index it and find out which are the planes to give you diffraction. I have one slide that will tell you how much time I can take. 20 minutes more. I have to press fast. Okay. See that when you rotate the crystal, there are some points far away. So you rotate the crystal, doesn't touch the sphere of reflection. Do you observe those reflections? No way. What is the possibility? You increase the size of this. For that you need to have a shorter wavelength range. That's why you use molybdenum the shortest possible. So you will have use chromium. You get very less number of them. The moment you use small and small radius wavelengths, you could get more and more data. That makes you more and more reliable your experiments and observation. Okay? So this is another important thing you need to remember, that Bragg's one concept will tell you what kind of reflection you can observe, what kind of reflection you see. Okay. Another thing is, I will go a little faster. There are factors that affect the intensity. Okay? Which are? So there are so many. What I am going to concentrate on is symmetry. What are all of symmetry in their intensity? Okay? Now, what are those symmetry absences? Symmetries will give you some kind of absence. You expect some reflection, but you observe the spectrum, they are white. That is because of the internal symmetry crystal. Then what is symmetry? As I said earlier, the lattice is constructed by a translation vector. Translation means the translational symmetry. You move it. So translation symmetry is very essential for a crystal. Without that, you don't have. So anything you do, if it violates the translation symmetry, you cannot accept it. That's why bipolar symmetry. You have never seen tiling with bipolar pentagonal tile. Okay? You can never kill this. Okay? So therefore, it violates the basic principle of the translation symmetry of the lattice, so you cannot. I mean, you learn in the textbook. Very simple thing. It's already there in the textbook. So what are the symmetries present here? Translational symmetry. Okay? There are other few more symmetries that will give you some kind of intensity modification because of this internal symmetry. This is called as lattice centric. You have screw axis and flight plane. They will influence the intensities drastically. There are 14 Bravais lattices. Remember? There are 3 different types of lattices, 4 different types. One is primitive, very simple. Only moderator. Right? Then you have 3 more different types. Okay, I will come to that in a minute. So look at this, what is symmetry? Symmetry is, what is that? Symmetry creates a replica of the object that we started with. Look at these replica symmetry, so beautiful. Because it has very high level of symmetry here. Look, there is symmetry here, there is symmetry there, 2-fold symmetry there. Look at this, Jewish symbol, highly symmetric. This is Yin Yang, Taoist symbol, then Islamic symbol again has symmetry in it. See? The star they made it like this, to have a 2-fold. Now it works like this. Then look at this, Buddhist symbol, highly symmetric. Shinto symbol, you have symmetry there. Sikh symbol, And so many Baha'i and then Hindu, all those religious symbols are made of symmetric, highly symmetric objects to make it beautiful. This one, you look at this, the nature also loves symmetry. Some kind of one-fold symmetry. The butterfly, it's a mirror plane, the star that is not exactly identical. Who created it? You say DNA. Then you say DNA created. But there is a mistake in that. Create lot of trouble. I don't have time. Okay. This again a rainbow. The natural phenomenon. It also has a two-fold symmetry or a mirror symmetry. Again, what not if you walk to symmetry? That is a light symmetry. Okay? So everywhere, the left hand and right hand you have a mirror symmetry. It's totally symmetry that is meant. And nature loves symmetry. Okay? The translation symmetry, rotation symmetry and inversion symmetry. They are the fundamental symmetry. Okay? You have mirror symmetry also. You have combination symmetry, true and right. They are the combination. All these symmetries will influence the crystalline nature. And again, the 7 crystal systems are based on the symmetry consideration and nothing else. So, okay. This is a Williams picture telling you the stereographic projection. Good old days when the computer was not available. They see pictorial representation. But whatever the symmetry available in this object is projected onto the plane. And what is that? When you join in the school, they teach you something. With that you will use the whole good old thinking power. And you will be tuned to what the things are being taught according to what is there in the system. No other way. You want to get marks, that's only. At the expense of your free thinking. Okay. I'm going to show you further. This wallpaper is made up of 2 prototypes. White and red words. But do you find a repeat in it? Which one is the prototype? Don't know. Is there any possibility? Is there again two types of pictures? One this, other one. Same time, but different colors, different speed. What is the basic repeat? Then look at this. There are 3 objects. This is a turtle, we have a pigeon, and there is another fish. We have a 3-fold there. Very symmetric. But what is the repeat? Can you find the repeat? Of course, it is possible. Look at this. It's not one right fold and left fold. But if you take this one as a single unit and repeat in 2 dimensions, you will have the entire picture could be created. Okay, this is not a problem. When you coming to this, is a 3-dimensional one. Again, you have the repeat. Okay, that's the origin of the unit cells. Different kinds of early rate of cement. Okay, then look at this object. What is it? D6, H6. What are the symmetry elements present in? There is an inversion symmetry. There is a 2-fold symmetry. There is a 2-fold symmetry like this. This is 6-fold. You have 3-fold symmetry also. The group theory will tell you all those symmetry elements present in it. Okay? And of course, the identity element is present with every object. Now you see that this is the mirror. You take this cross section, the mirror against this another. Lot of symmetry elements that make the appearance of this molecule peculiar. So what is rotational symmetry? All learned it. Look at this. This is a rotation matrix. You do a rotation with respect to Z axis. This is the Z axis. I took this is the Z axis. This coordinate will not change, but other 2 coordinates will change. The transformed coordinates will be, these are the original coordinates. These are the transformed coordinates. This is the rotational matrix. If you put 180 the 2-fold, theta is 180, 360 1-fold, 120 as 3-fold, 4-fold, etc. You can put different values for different rotation axis and find out the equivalent position. Okay? Those points generated by them are equivalent. You do the operation, you get the superposition. Now, coming to the mirror symmetry, this is what? This object has a mirror, this one, this way. Okay? A plane, mirror is an object, symmetry operation with respect to a plane, whereas the rotation is with respect to an axis. Okay? So you have a mirror plane perpendicular to the object. Then what is that? This part and this part is related by a mirror symmetry. This is the old coordinate, this is the new coordinate. What is the symmetry matrix? This is the one. Okay, if you have a coordinate there, only x coordinate will change if it's perpendicular to a axis. It's perpendicular to b, only one coordinate. Okay, the mirror image is so beautiful and so confusing. You have a pimple on the right side and you want to squeeze it in a mirror. You always squeeze at the left side, not on the right side, because it is the angle of the image has changed. Okay, so this is the actually these two objects based on 2 points, this and this both are identical by this mirror property. Now you have inversion symmetry. You look at this object, so every plane there is another plane. Plane is by a center of symmetry, that's through a point. Okay, so this is the transformation method. Now, influence of symmetry on the structure factor. What is structure factor? That will tell you the total intensity of the wave scattered from a unit cell in a given direction. Remember, I can't say anything more. Okay? Structure factor is the total wave scattered from a crystal in a given direction. When you say HK, it's a direction, isn't it? HA star plus KB star plus H. That's a direction. So in different directions when it comes out, you have indexes, different waves. Okay, that is a structure factor from entire unit. And there is another name, what you call it as atomic scattering factor. Now Thomson scattering. They were given down. Thomson's formula will tell you what is the scattering strength of an atom in a unit. That is what is the atomic scattering factor. They are different. How much an atom scattered? That is atomic scattering. How much the unit cell scattered? Unit cell will have so many atoms in it. All of them together, how much it scattered is given by the structure factor. These are the two different things, just remember. But how do you calculate the structure factor? Look at this. This is the atomic scattering factor. There is an amplitude as well as a phase. The phase of the wave scattered from a unit cell in a direction is KL given by exponential phase 2 pi I hx plus ky plus n. HKL are in the unit cell. And x, y and z are atomic positions. Suppose an atom is at 1, 1, 1 or 0.1, 0.2, 0.3 in an atom or 2 angstrom, 3 angstrom, 4 angstrom in a unit cell. If you put those values for all the atoms and put together sum up, you get the total structure factor. So structure factor is the combination of all the atoms in the unit. For a primitive unit cell, how do you calculate? Primitive unit cell, though there are 8, each corner is made by 8 adjacent unit cell. Ultimately, the contribution to this unit cell is only 1. Take this as the origin. Okay? So what is the structure factor equation? Only one atom, put it as J, and then put X, Y, Z as 0, you get 1. So it is atomic scattering factor. What does it tell you? AB is independent of the scattering plane. Any plane, you have the same intensity. Now coming to base and it's another datum. Apart from this one, you have another atom at the base. Phase center. One of the phases center. Okay? This phase is shared by 2 such units. And there are 2 such units. There is only one point, the water source is in itself, and these are the coordinates. When you put the first one, what you see? The 0, 0 goes like this. Second factor, this half, and this goes there. But you get sum up, you get like this. The peculiarity here is that when h plus k is odd in a scale plane, when h plus k is odd, what do you get? This becomes minus 1, isn't it? N5 when it is odd, it becomes minus 1. Therefore, 1 minus 1 is 0, you don't get scattered in it. Okay? These are those planes 1, 0, 0, 1, 0, 1, 1, 0, 2, 0, 3, 1. All these planes do have h plus k odd values, therefore we scattered in them. Yeah. Provided they are even, then you get the maximum scattering. Similarly, when you have a body center, it is exclusively at the center. Apart from 0, you have half, you get discontinuous. This takes odd values in the answer, when it takes even values in the answer. That is how every alternate reflection in certain crystals are the same. Immediately you can identify that it's a body centered lattice. Okay? Now coming to phase centered. Every phase is centered. So you have two more positions. This, and this. When you calculate the structure factor, you get like 0, you get 1. Okay. Second one, x plus k plus l. This is okay. K plus l plus h. You get 3 k. When you have mixed values, even or odd, mixed together, you get one of them will be positive, other will be negative, so that the same effect. They take all of them, even all odd values, they will remain. Therefore, you get maximum scattering. They are mixed. They are mixed, then you get 0. That is why 1 0 0, 2 1 1, 2 1 0, due to all these will be missing. Pattern. You will wonder why this is happening. Okay? This is the condition. So then, when you have sodium chloride like kind of thing, again say FCC, the lattice is different. You can see that. Okay, I will go. Staring at stuff. Now, two conditions. Even if that you work out, you get the equation like x plus k plus n is odd value. Even the scattering is possible, even they are unmixed, you get this one like this, you get, and this odd, so you remember that, unmixed you get maximized. Even if it is unmixed, the structure factor expression becomes like this. Then this is the condition, okay? Plus, the sodium, structure factor sodium and chlorine, this is the structure factor, atomic scattering factor sodium and chlorine minus. They are different. So for sodium and this sodium chloride, you get these reflections. Suppose it is potassium chloride, K plus and Cl minus, you have the same number of electrons in it. K plus and Cl minus, they are 18, both are 18. Therefore, these reflections will be absent. Now sodium chloride and potassium chloride having the same kind of structure, same unit cell. If you look at the diffraction pattern, there is a small peak appears for sodium chloride in these two positions. For potassium bromide, that will be absent. Potassium chloride will be absent. Okay? These are called the symmetry absence. Okay, summarize over there. I will tell you diamond cubic has a different thing. I don't tell. When you have screw, what is screw? You have rotation plus translation. Okay? So these are the coordinates. And then you put this. This is just for the rotation, this is for the translation. Okay? I will go. Okay. You have light plane, then you have the symmetry operation like this. You put this again. Okay. Indexing, when you come to the indexing part. Sorry for skipping few things. Okay? When you index it, you find that for 7, you don't find a choice. Because you don't have a plane corresponding to H plus But when you come to 9, you have two possibilities. These two planes lead to the same heat. Again, there is another problem. Two reflections give you the same intensity, same position they intensity. Obviously, they have to be different. Okay? So that has to be found out. Again, 17, 18, you have the same kind of thing. All these problems have to be sorted out when you index a diffraction pattern. That is only when you come across a new system. Old system it is okay. You have, okay, summarizing all these systematic absences. Okay. I'll go the simplest thing for the structure examination is this. You have X-ray, maximum wavelength, because just like a room sitting, people filled with, somebody could come through the door and see what is there inside. Okay? If you say an elephant to come inside and see what is there inside, elephant cannot come through the window, door, and cannot interact with the people, cannot go in between. But X-ray being small, I could go and ask the people, where do you come from, what you do, and what you are, everything I can collect. X-rays will do that. Interact with the atom. When it comes out, scattered, it's coming out, isn't it? It comes out, you ask them what you have made, because our ordinary light cannot go through it. Wavelength is so huge that it cannot scatter it. It just skips the unit. Okay? Therefore, X-ray is the same. The problem is, X-ray language is the rule. Like a Chinese fellow getting into the room and finding out people and coming out thinking, what do you learn? You need to have an interpreter, isn't it? So what is the concept? X-rays are going to the crystal with a density in it. It scatters, it comes out. You ask the scattered ray, what is there in it? It will tell you. And the interpreter will tell you, now this ray is telling like this, there are several people in it, somebody is speaking and some people are listening, some people are sleeping, some of them are understanding, things like that. So you get a picture of what is going on inside. Okay? Now the concept is that you have scattered rays. In the normal imaging, what you do, you have a lens that will focus on the focal plane, you get an image there. But here the image formed is a different language. And unfortunately there is no material which has a proper refractive index to focus X-ray. Now fortunately we have lens, what is called the Fourier transform lens. Fourier transform will act as a lens for X-ray. In fact, that will focus it to electron densities. It's again a lot of stories, how many calculations and things like that. But anyway, this is the nutshell of how to do molecular image. Okay? Now, ultimately you get like you have structure. The simple thing, but we did complicated things, everything you can do. Huge molecular mechanism. Okay, can I go ahead or stop it? Okay, there are unusual symmetry. C60, 4 rings. Heard of 4 rings? Polar ring is C60. What is the symmetry of it? What is the symmetry? Icosahedral symmetry. Icosahedron contains a 5-fold symmetry. Look at this. This is an icosahedron. There is a 5-fold symmetry. But we learned that 5-fold symmetry is not possible because it violates the transference symmetry of the diamond. How come it is possible? That was the question which couldn't be answered for long. Anyway, I will not tell you these details. The details are there. Yeah, there are 5 light-emitting solids that we come across in solid state. What is that? Nano regime. We have metal clusters. Often we come across very small metal clusters. They fall into this category. These 5 objects are called light-emitting solids. What is that? The reason? Phases. Number of phases minus number of edges will give you plus the vertices. That will give you a constant of 1. It is 2 for all these. Number of phases, number of edges plus vertices. That will give you a constant quantity for all these solids. Call them as electronic polycrystal. Okay. Now, this is icosahedron. How many? 20 identical equilateral triangles, 30 edges, 12 vertices. One of the 5 electronic solids. You have 5-fold symmetry, 6-fold symmetry, 3-fold symmetry, and 2-fold symmetry. All of them are available in this. The tetrahedron, you come across the tetrahedron, 4 triangles. Okay? So, here, this is information just learned. Now, this is a octahedron. The octahedron coordination of sodium chloride. Every sodium is connected with 6. The kg of 6 fluorine in an octahedron coordination. The word is also the same. Okay? That is what is octahedron. Okay. I'll add here. This is a simple thing. This is a cube. You know the cube. What is the characteristic of a cube? Anybody? What is the symmetry to characterize a cube? 4-fold? As a plane, square plane, is a 4-fold? No, the answer is no. You have 4 3-fold axes. Body diagonal is a 3-fold. You take a cube, some of your younger brothers will have a cube to play in the home. Take out and rotate it along the diagonal. Diagonal is a 3-fold. You have 4 3-folds. That is the characteristic symmetry of a cube. 4-fold is available with a square, tetrahedron. Tetragonal space to have the 4-fold. The cube can never have 4 3 other than 4. Okay, so symmetry is quite interesting. This is the dodecahedron. Now 5-fold symmetry, only 5-fold. Okay, these are again another planet solid. All these files. This is how I tell you the story. This man has finished. We see Shesman, Danny Shesman. He proposed a theory in 1984 saying that he says in a very remarkable statement after getting the Nobel Prize. What is that? A good scientist is a humble scientist who is open-minded to listen to other scientists when they discover something. But people never listen to him. That's why he said, such a desperate statement after getting the number size. Why he said that? Look at this. As I said, dipole symmetry is possible. It's a quasi-crystal, not normal. Quasi-crystal, really, now dipole symmetry. This is a kind of Penrose styling. You have two types of prototype. One is the red one, other is the grey one. Instead of single one, you have two types, you can fill them there. Where the symmetry is different. Okay? And if you take a Fourier transform, you get like a beautiful diffraction pattern. The reciprocal space of this is that. See, a quasi-crystal is a crystal with a forbidden symmetry. Not real symmetry, it's a forbidden symmetry. They have a long range symmetry, but short range you don't have. That's the problem. I will come to that. Okay, it's a comparison between quasi-symmetry and the real symmetry. Go into that. Finally, what I want to say is that we found this in 1984. The bipole symmetry in a mineral, a combination of aluminum and some other thing. The crystalline form we found the diffraction pattern having a bipole symmetry. People told him you are mad, bipole symmetry is not possible. You are checked out of his lab using some display, Marcy laboratory in UK. They will scolded him, then now come many conference proceedings and things like that. He was not allowed to speak. Everybody said that because of this, he published this in the Physical Review letter in 1984. Not very high journal, ordinary kind of journal. He published ultimately. Some people said that okay, accept whatever he said and publish with that. Look at this. He wrote in his book the confused. Actually, it was a 5-fold, he ratified. Okay? This is a 5-fold symmetry in the diffraction pattern. So until 1982, okay, people cannot accept the 5-fold symmetry in the real system. And the concept of the quasi-crystal was not existing, was not known. That was the problem. Okay? Now, the Penrose styling, the quasi-crystal pattern. Okay? Again with two prototypes. Again, okay, anyway, I don't go into those things. See, in 2009, Alps Mountain, they found a mineral, natural, what is that, mineralogist. Natural mineralogist. They found some material in Alps Mountain. And they put it to him. The first thing what they do is take the material, put it like X-ray exam and check what it is. The mineral is maybe what is known or unknown one, something like that. So put it to the diffraction pattern, found surprisingly that's very cool. Very similar to what Texas suggested several years back. Then people realized that bipole symmetry could exist and it went to science. 84 when he said, it went to Physical Review. But now it went to science. Then people realized the importance of it. This is the crystal actually. The mineral they got, they put out small tip of it and analyzed. This is what the diffraction pattern finds. Bipole symmetry, kind of a quasi-diffraction pattern. And he was awarded the Nobel Prize in 2011. He has to wait for so long, even after telling truth to the world. Like it's like a world in which everybody is mad, you alone is not mad. Finally, you have to admit that you are also mad. But he did. I think the story is enough. This is what this kind of combinations of metal element give you. Or they could still very good application. Anyway, I don't have time to look into this. I thought I would tell about this man's work. You know what is ribosome? The machinery that makes protein. The Indian word. Do you know? Ramakrishna is an Indian. He did. No. Anyway, forget it. This is how proteins are made in our body. Every living organism makes protein through ribosome, the machinery of ribosome. You must have heard of tRNA and messenger RNA, codon and decodon. Then it is good time. Like this. Tell you an animation, this will tell you, this is a small one, big one. When they want to make a protein, they unite. Then the messenger RNA will carry the information from the DNA. It comes the message with what is a codon and fix there. This is the messenger RNA. It moves. Next one comes and finds there. Then try to synthesize the protein. Okay? So what he said was, he could explain the mechanism of protein synthesis in every living being. The transfer RNA comes with a monomer, gives to the machinery of ribosome, and the ribosome will stitch different amino acids getting a polymer, natural polymer. You know the importance of biopolymers. Without that, we can't live, we can't think, we can't move. That is very important. Make a mistake, you will get a disease like sickle cell anemia, deficiency of oxygen carrier, capacity of hemoglobin. Okay, we have porphyrin, things like that. So many materials made out of this kind of concept. Okay, so this is the mechanism. It goes into the cell and finally it becomes a. What is the importance of the work? You will see that it goes through a tunnel in the ribosome. What I am saying, it goes through a tunnel. What is the significance? Okay. What you do is you, I don't have a couple of, I removed a couple of pictures. They complex with antibiotics. Tetracycline, tendabilis, so many medicines are there, but you eat tetracycline, chloramphenicol. What they did was those molecules go and bind there. They block the pathway. So even if the organism synthesizes the protein, doesn't allow it to go through the tunnel. So it stops production. So you could kill the microbe. You could make the microbe go to multiply. That's the thing. Your synthesis, remember, Ramakrishna was a physicist. He did PhD from Ohio University in theoretical. Then he worked on biological problems. The biological problem. He got Nobel Prize in chemistry. And immediately after his invention, people started making medicines out of it. So, physicists turned into biologists, structural biologists, got Nobel Prize in chemistry, and his application of the work has gone to medicine. That's the way we integrate different organs. Don't keep patients towards this science. Every branch of science is good. Maybe you don't understand it, actually you don't like it, or you don't find it interesting. Don't blame it. Okay? That's all. We have facility for doing X-ray structural analysis and other things in our university. We have analytical dissectors, high temperature, low temperature attachments and things like that. Crucial systems. We have software for structural studies for central organ powder and also hepatitis. Anybody who wants to be are welcome. Also that the colleagues over here for giving me an opportunity to present this work. And also I did not show any of my work, but it will be in between. So I thought let's be some foundation of that, so that therefore if you find interest topic you can identify words. Thank you for your patience listening. If you have any questions, I can answer.